Having stumbled upon this video, I presume that you, dear viewer, find yourself looking at a polygonal sticker adhesively bound to yet another polygon, most likely in the form of a street sign. In this case, I bid you good welcome and ask that you grant me but a moment of your time that I might impart a small bit of knowledge concerning polygons and some commonalities which are shared among all such two-dimensional figures.
What? Hey guys, what's up? What Sheldon is trying to say is let's look at some cool objects we all see every day.
You see, polygons, which, for our purposes, can be defined as a finite collection of line segments, each joined at either end by yet another line segment, the connecting points being the vertices of said shape, wherein all lines being connected create a closed loop.
Yeah. What he means is things like a sheet of paper, an index card, a stop sign, or even a license plate. So squares, rectangles, triangles, pentagons, or octagons all complete a loop. So they must be a polygon.
A common question concerning such figures regards the summation of their interior angles, those being the angles formed at each vertex that lie within the polygon itself. This problem is of import as it allows us to ascertain the value of each angle in a regular polygon, as well as to define the properties of the shape using trigonometric means. But I digress.
Is it just me, or do you really love hearing yourself talk? So, we want to find out the total degrees inside the polygon. Why don't we first count the number of sides that the polygon has? The number is the same as the number of angles that are inside the polygon.
It is common knowledge that all triangles in the Euclidean plane have interior angles that combine to 180 degrees. This can be shown quite simply. If one line of any given triangle is chosen and a parallel line drawn tangent to the vertex opposite of said line, then, using Euclid's proposition concerning alternate interior angles of parallels, it is clear that the angles of the triangle are equivalent to that of the straight line, which is, by definition, 180 degrees.
Or we could just divide a rectangle from the upper left corner to the lower right corner. We all know that a rectangle has 360 degrees inside its perimeter. So if we split it in half, we have 180 degrees. That seems easy enough.
Having established this simple fact, we can see that any polygon can be broken into triangles, it being assumed that the polygon sides are not curved. For a regular polygon, this quantification can be obtained by drawing segments that connect one vertex to all other vertices within the polygon.
I just said that a second ago. It just broken into a lot more triangles.
This process will not only divide the polygon into triangles, but the number of triangles will always be 2 less than there are sides of the initial shape. Not only this, but also the angles of each triangle will align perfectly with those of the polygon, such that, to find the sum of the shape's angles, one needs only sum the angles of the constituent triangles, each of which is equal to 180 degrees.
Very good. That makes sense to me. Plus we can always draw them out and see it firsthand.
In other words, given any polygon with n sides, we have only to subtract 2 from n, multiply the difference obtained by 180. The resulting number will give the sum of the interior angles, which was our initial goal.
Wow. Even I don't have anything smart to say about that. I like it.
Moreover, this process works for all polygons comprised of straight edges, so the shape need not be regular or even centered around a particular point, but can be as amorphous as you would like, so long as the sides do not overlap, it being two-dimensional, after all.
So, this works for all two-dimensional shapes with straight sides. That's pretty cool and straightforward.
And there you have it.
And there you go.